Okay, welcome to lesson 38, the last lesson of this week. We also have a bonus example here at the end. So we're looking at Z procedures for two sample proportions. So we're looking at two populations. We want to compare a proportion across two populations or two groups. Okay, so when we want to use two proportions Z-test, it's when we have two populations or groups we're interested in comparing, and specifically we're interested in comparing a proportion between the two groups. So we're going to test the difference between proportions P1 and P2. Note if you use subscripts like 1 and 2, we will require that you label what 1 means and what 2 means. So keep that in mind. We will jump on that every time. And then you'll do P1 minus P2. Are you allowed to label them differently so it's effectively P2 minus P1? Yeah, just be careful. You need to keep track of which order you subtract in. So our conditions here, we're going to go ahead. We're going to stick with representative samples. Super important. The easiest way to get there are to take random samples. I did add here, it is important that we have independent populations. So if you have two groups you want to compare, you want to make sure that the individuals in sample 1 could not possibly be in sample 2 as well, that you sampled from totally independent populations. And then for here, it's a lot easier to do it this way. We're just going to go ahead and make sure that we have at least 10 successes and at least 10 failures in both samples. This will effectively work. So once again, you can have a lower one-sided. You think maybe this would be if you thought the proportion in population 1 was lower. So P1 minus P2 was less than 0. This is similar or the same as P1 is less than P2. We do like to have it set up this way because there's our null value right there. That null difference is 0. Upper one-sided, this is where you think, oh, P1 is greater than P2. If you just added P2 to both sides. This one, you're just saying, hey, let's just see if they're different. I don't have a suspicion one way or the other. I just want to know if they differ. So here, there's going to be a little bit of a difference. The part that goes under the square root will be different. So the numerator will be similar. What I saw in the sample, so the difference in proportions I saw in the sample, minus the claimed amount, almost always is going to be 0. We're just going to treat it as 0. That's always, it's unusual that it's not. But then this standard error here on the bottom is going to be different than it was for the confidence interval. So I definitely want to stress that in this week's content, the standard errors are different for confidence intervals versus hypothesis tests. So if you're dealing with proportions, you need to be wary of which one you're doing. So specifically, we assume that the null is true in order to calculate the test statistic. So this implies that P1 and P2 are equal to one another. So you could even rewrite this as, where do I have room? That P1 is equal to P2, which is equal to the total overall proportion, right? So if they were the same as each other, they're equal to some overall proportion. If you pooled them together and took the total number of successes over the total number of observations, that would be your P total. We estimate it with P hat T. So take in your sample the total number of successes in both samples over the combined sample size. That's your P hat T. And you have to use it here in your test statistic because in order to calculate a Z-test statistic, you have to assume the null is true. So that's where P hat T comes from. It's kind of like saying we're assuming that P hat 1 is equal to P hat 2 is equal to P hat T. If you plugged in P hat T for P hat 1 and P hat 2 of the other standard error, this is what it comes out to. Okay, so we're still very much stuck on the extraterrestrial belief example here. So we have a survey. They went ahead, they did some surveying. They took 100 randomly selected Americans that were college educated. They took another randomly selected 100 that were not college educated, and they asked them do you believe in life outside of Earth? 35% of the non-college people said yes. 47% of the college-educated Americans said yes. So here's in this is where our question is based on these data, because data are plural. Is there evidence that the proportion of college-educated Americans that believe in extraterrestrial life is different from non-college educated? So different. This tells me I just want to know if they differ from one another. I don't necessarily think one group is higher than the other. I just want to know if they differ. So my question for a z-test or hypothesis test, it should always be in the form of a yes or no question. So is the proportion of college-educated Americans that believe in extraterrestrial life different than the proportion of non-college-educated Americans that believe in extraterrestrial life? Just as a reminder, I'm labeling college is 1 and no college is 2. Strictly out of preference, a lot of us just prefer to subtract so our point estimate's positive. So my parameter of interest, so college, I always think that it's college minus, no hats. Oh my gosh. Non-college. So I just wrote something goofy up here. Never, ever, ever put hats in as your parameter of interest. Parameters will never have hats and they'll never have bars, as far as we're concerned. So if I asked in notation, this is what we mean, the P1 minus P2. If we ask for in words and context, we mean the second part. So the difference in proportion of people that believe in extraterrestrial life between college-educated and non-college-educated Americans. Since I said difference in proportions, I absolutely need to specify the order I'm subtracting in. You might have noticed that I'm skipping over the inventory because I'm going to put it on the next page. There's really just not a lot of room on this slide to also write that. So keep that in mind. I will include the inventory. A significance level. So here I did a 90% confidence interval. I'm going to do a 0.10 because I did a 90% confidence interval. But within reason, if you read this problem and it had nothing in it, it would be okay for you to pick 0.05. Most of the time, we will be specific and we will tell you what we want. So my hypotheses, okay, not the next slide, that's not where I'll put my inventory. I'll put it on the other. So P1 minus P2, so just a reminder, college is 1 and no college is 2. And we are going to say by default, their difference is 0. This is the same as saying, hey, P1 is equal to P2 is equal to some overall proportion, right? There's no even need to keep them separate. And then my alternative, this is based on the prompt. So I'm going to have, this is my parameter of interest. This is my null claimed difference. And I just want to know different than, so not equal. So here, we kind of did this a little bit here. Independent populations. I'm writing that in. That is really important. So are our samples random and representative? Yes. Although I'd love to see the master list that they used. They randomly selected, from non-college educated Americans, and they randomly selected from college educated Americans. What master list did they pull from? I mean, that's kind of unusual. But we're being told that they did that. So yes, we're saying that's met. Independent populations, we kind of went over this earlier. We said, hey, no individual can belong in both groups at the same time here, based on their definition of educated, probably. And then also, we did cover this base earlier. do we have at least 10 successes? So at least 10 people that believe in extraterrestrial life in each group, and at least 10 people that don't believe it in each group. So I had college, I had 35 people, sorry, no college. I had 35 that believed, I had 65 that didn't. Yes, those are both greater than 10. For college, I had 47 that believed, and I had 53 that didn't. Those are both greater than 10, so I'm good. Yes, we're good to go. So here, calculate the test statistic and p-value. This is where I kind of anticipated there would be more room to write. So I am going to go ahead and put my inventory here. So remember 1 and 2. So p hat 1 is equal to 0.47. P hat 2 was 0.35. P hat, no, let me see, N1 and N2 are equal to each other. They're equal to 100. I'm going to stick here P hat T. So I now, one thing that's majorly different from the other ones that we did is we have to estimate this overall total proportion. So the number of successes, so I need to add 35 and 47 over their total sample sizes, so over 100 and 100. So I get what, 82 over 200, is that 0.41? So what this is saying is if I totally ignore which group people are in, if they're in college versus no college, 41% of everyone believed in extraterrestrial life. If the null is true, and there's no difference between the groups, that means the proportion in college, or not in college that believe in the life, and the proportion in college that believe the life, those proportions should basically not be statistically significantly different from 0.41 if the null is true. So also, if the null is true, this is centered at, so P1 minus P hat, P2, no hats, is equal to 0. What did we actually observe? So I'm going to put it here. So P hat 1 was 0.47 minus 0.35. This is my, so 0.12 minus 0. This is my point estimate. Oops. I'm combining words now, making up words. Over here. So what's really important is I now need to stick this 0.41 under the square root part. So 0.41, 1 minus 0.41 times, this is really, really sweet that the sample sizes are the same. Makes it so much easier. There you go. So there we go. So notice because of the way I chose to, the direction I chose to subtract, I'm going to get a positive z statistic. You would get the same one-sided p-value and everything if you went with, if you had subtracted in the other direction. You just would have gotten a negative. So I end up getting positive 1.73. If you had subtracted in the other order, you would have gotten negative 1.73. So looking here, if the null is true, it's the difference in proportions for the population is 0. But what I saw in my sample was 0.12. So I want to go away from the middle. So anything that's, negative 0.12. 0.12 or further away from 0, that's going to be something that's as or more extreme than what we saw in our sample. So remember, it's two-sided, so we have to add both those areas. That's why we find the one-sided p-value and multiply by 2, because it's perfectly symmetric. It's so nice. So 1.73, labeling here. We can break that up into 1.7. It tells me which row to use. 0.03 tells me which column to use. Where it lines up, remember this table gives me area to the left. I just declared right here, I want this top tail area, I want the yellow area, so 1 minus 0.9582, but 0.0418. That is the sound of me doing mental math. It looks like it worked, so one-sided p-value is equal to 0.0418. Then you have to ask yourself, looking at the alternative hypothesis, so P1 minus P2 not equal to 0. It's a two-sided test, so I need a two-sided p-value. So multiply both sides by 2. So I'll get a two-sided p-value, and that'll be equal to 0.0836. So I get a two-sided p-value of 0.0836. So if the null were true and the difference between the proportions for these two populations really was 0, I would see a difference in sample proportions when I take samples of 100 of 0.12 or bigger in either direction, about 8.36% of the time. So here, I'm going to plug in, I like plugging in the values and then saying whether I reject. 0.0836. It was a z statistic, 1.73. Totally, you would have gotten the same thing if you had a z statistic of negative 1.73. We used the significance level? I'm totally blanking. It's a 0.10. So looking here, I want to compare this p-value to the significance level. If the p-value is smaller, I'm going to reject. If the p-value is bigger, I'm going to fail to reject. Looks like here, 0.08, it's less than 0.10. So, oops. I'm going to reject at the 0.10 significance level. If it had been the 0.05 significance level, we would have failed to reject. So just know that. Totally depends on the significance level that you set ahead of time. It does need to be set ahead of time, though. You can't find how much evidence you have and then decide what your significance level is. That is cheating. So there is, and this is kind of a weird spot because it's not super strong evidence. I wouldn't say it's strong. Moderately strong is kind of pushing it. Some I've seen like slightly suggestive. We took that off of the thing, but some moderate. It's not a lot. Evidence that the proportion of, and then I'm still going to write this in the same format that I was writing the confidence interval. So population 1 is, I did college educated Americans was my first group. College educated Americans, technically it's all proportion of all college educated Americans that believe in extraterrestrial life. Terrestrial life is, so whatever the alternative said, we were looking at different, so different than the proportion of, now we have to say the population too, so all non-college educated Americans, that believe in extraterrestrial life. This is one of those things that typing it probably actually goes a bit faster. Oops. So, putting it all together, this is my two-part conclusion for the hypothesis test. So the first part is this part. we reject the null hypothesis at the 0.10 significance level. I say what the z-statistic is. I say, is it a one-sided or two-sided p-value? And I give the value. In the case of when we have T procedures, it's okay to give a range of values, but we can be, honestly, if you're using R, you can be more specific. Then we're going to talk about, okay, well, there's some or moderate evidence that the proportion of all college-educated Americans that believe in extraterrestrial life is different than the proportion of all non-college-educated Americans that believe in extraterrestrial life. So that is what we concluded. This hopefully isn't too surprising because when we did the confidence interval, we did note the entire interval was above 0, which meant that 0 was not in the interval. This suggested that the difference in proportions was not equal to 0. So if you look at your confidence interval and your null value is not in it, it's not, you're probably looking at, you're going to look to reject the null hypothesis that it's not equal to that value because your confidence interval is saying, no, these are my plausible values. If you're not in here, I don't see you as plausible. So, yes. We have one more example, just for practice. Thought this would be handy. So we have a hospital in particular, although I don't know about now. Everything's a bit different right now because, as you can see, nothing's delivered in person right now. Although I did hear that they're talking about making the second summer session start in person, at least right now. So we have a hospital. They offer a first responder course. You get certified after you take an exam. They go ahead. Right now what they are doing is they have a traditional course. It's delivered in person. It's twice a week. It's given for 10 weeks. There's lecture and practice. But this particular course is really, really popular. A lot of people want to get certified. So they said, hey, let's try this new hybrid delivery method. So the hybrid delivery method is still a 10-week course, but they meet once every 2 weeks for practice. So not twice every week, but once every 2 weeks. So a quarter of the time roughly, and for practice. And all the materials and lecture are online. So they go ahead, the hospital randomly assigns 95 course registrants to the traditional course that has the lecture or the hybrid course. I don't think that would go over very well in real life. People have a tendency to say, no, I don't want to take a course that way, and they drop it. But hey, supposedly they did this. So they go ahead, they take those registrants. So just right off the bat, the fact that they have 95 of them means we will not have equal sample sizes, right? Hopefully. Not an even number. So they want to determine, hey, if we have enough people pass their certification exam, actually, no, it's more of the other way. So if the hospital determines that people pass the exam less often, if they take the hybrid course, they're going to talk about discontinuing it. They're going to say, no, it wasn't successful. We don't have people passing at the same rate. This is not good. So we're looking at the proportion of people in a class that pass. So this is my traditional class. I'm going to call this 1. My hybrid class, I'll call this 2. So there were 47 people in the traditional class. 37 of them passed. So p hat 1, it's about, I rounded there, 0.787. So like 78-79% of them passed. In the hybrid course, 48 of them took the course, only 30 of them passed. So my p hat 2 is 0.625. So that right there, that's a lot of my inventory. My sample sizes, my p hats, that's a lot of my inventory there. Okay, so the first place we're going to start, we're going to state the question of interest. So what is the question we even want to answer? We don't want to do all this analysis and have no idea what the question is, because what the heck are we doing? So this is a hypothesis test. It should be worded as a yes-no type question. So is there a difference in proportion of people that pass their certification exam between all students that take the traditional course and all people taking the new course? So I didn't specify which direction I was subtracting in. So I'm going to do traditional minus hybrid. And quite honestly, that comes down to preference. I did that because I like, when I have my point estimate, I liked it to be positive. Absolutely nothing wrong with subtracting the other way. The big thing is, if you talk about, oh, I'm looking for the difference between A and B, you need to tell us what order you're subtracting. Is it A minus B or is it B minus A? You have to tell us. If you want full credit, you have to tell us. So then my parameter of interest, first I will write in notation, so P1 equals P2. So this is, it's really important to tell, like, 1 is equal to traditional, 2 is equal to hybrid. You must tell us that. So then the difference in proportion of people that pass their certification exam between all students that take the traditional course and all people taking the new hybrid course. I know, beating a dead horse kind of saying, but I'm going to write that direction I chose to subtract in again. So I'm doing traditional minus hybrid. Then don't forget our inventory. I did include spots for all. All of these pieces are on the last slide. So we had 37 people in the traditional course out of 47 that passed. So 37 over 47. And we rounded to 7.787. In the hybrid, so traditional hybrid, I had 30 pass out of 48. So P hat 2 is going to be 30 over 48. That was a 0.625. Yeah, 5/6. Or no. 5/8. Yeah. Then, because I'm doing a hypothesis test, I do need to find out what is the overall proportion. So if I combine people regardless of what group they're in, what proportion of everyone passed their exam. So 37 plus 30 over 47 plus 48. So it looks like 67 people out of the 95 passed their exam. This comes out to what, 0.705. So about 70.5% of everyone passed the exam after they took the course. And if the proportions are really the same, that means the proportion for the first group and the proportion for the second group are basically going to be really close to the overall proportion. If they're not, that's a good indicator that, hey, wait, maybe they aren't equal. And so then my significance level, I believe it said on the last slide, it's 0.05. It's one of those I didn't include everywhere, 0.05. There we are there. So my hypotheses, so I'm just going to continue to say, okay, 1 is traditional, 2 is hybrid. I know, probably over the top, but it's super important that you label. So P1 minus P2. The null, remember, is saying nothing interesting is going on. Let's just assume they're the same. So I have an equal sign, and that null claim difference is 0. Almost always it's 0. It's going to be for us. For the alternative, so I'm still going to have the same null value, same parameter, but now I need to take into account what they are interested in. So they specifically were interested in So here, if the hospital determines that people pass their certification less often after taking the hybrid course, so hybrid is 2, 1, so P1 minus P2. If P2 is smaller than P1, a bigger number minus a smaller number, that's going to be positive. So this tells me I need a greater than sign. So greater than sign here. Because interested in P1 being greater than P2, right? P2 being less than P1. That's the idea. So this is what we started with, work backwards from there. So once again, independent populations, or independent groups there. So are our samples random / representative? So yes and no. The samples, meh, right? Probably the people that go through these programs don't select to do them at random because, I don't know, most of us don't sit around and go, oh, I think I will do this EMT training like at random, right? Especially if it costs money. The sample may not be random. Oops, sorry. I keep hitting the mic thing. However, we did use randomization. So not having random samples, that's like worth a disclaimer saying, hey, this may not represent everyone that takes this course. Because we don't know if it was a random sample from everyone taking it. Because honestly, it was probably just a sample of everyone taking it right then. Randomization, what that tells us, this is an experiment, and we assigned which course students would take. We can actually say the differences we see between the groups is because of the course type. So hybrid versus traditional, whatever difference in the proportion of people that pass, we can attribute that was caused by the difference in course type. So yes and no for number 1. So based on the central limit theorem, do we know that we have big enough sample sizes for p hat 1 minus p hat 2 to be approximately normal? So looking at sample 1, we had sorry, I'm going to write this somewhere. We had 37 successes, or people who passed, which means we had 10 people that didn't. That is greater than or equal to 10. Barely, right? By the skin of our teeth. Barely. The hybrid course, we had 10 people pass, which means we had 18 people not pass. That's both at least 10. We're good. So for 2, barely, but yes, we meet the requirements. And then independent, yes, so unless we had people who signed up like for both the hybrid and the traditional course, we don't have anybody who could possibly be in both. So this would be satisfied. It becomes much fuzzier the second you have people like signed up in both. But realistically, people usually won't. Okay, so now that we've sorted out, we meet the conditions, we have our hypotheses ready, we're going to go ahead and we are interested in calculating the test statistics. So I'm just going to write out again, so T for traditional, H for hybrid. Honestly, I usually would just use subscripts T and H for traditional and hybrid. So 37 out of 47 passed the exam. That was 0.787. 30 out of 48 passed the exam. In the hybrid course, that was 0.625. Then the overall, we had 37 plus 30, so we had 67 out of the 95 people passed the exam overall, regardless of what group they were in. That was 0.705. So things to note, if the null is true, so null is true, that means P1 minus P2, it's been a while, is equal to 0. That's the claim. So then what we observed, was this P hat 1. So I'm going to plug in here. So let me see, 0.787 minus 0.625 minus 0. I love subtracting 0. It makes life so easy. And then plug in the rest here. And then I'm going to calculate just the numerator there, because that's my point estimate. 0.295. Ugh, not having the same sample size makes this part more gross to do by hand, but most of us won't do it, all by hand. Just saying. There we go. So that's going to be equal to, well, the numerator. That's equal to 0.162. So p hat 1 minus p hat 2, what we actually saw in our sample is 0.162. Our alternative is interested in higher than, right? So we're going to go higher than. So we're going to want the upper tail. If you do the math here, it's going to look really weird, especially if you just did the last one. We get a z-statistic of 1.73. Is that familiar? It should be, right? It was the z-statistic in the last problem. And I tell you what, I could not have done that on purpose. It is really unlikely. So 1.73. So we just said we want to find this area. The table will give us this area. So 1.7 tells us the row. 0.3 tells us the column. So 0.9582. But then this yellow tail, it's going to be 1 minus 0.9582. It's 0.0418. So my one-sided p-value is equal to 0.0418. And this is where you stop and you ask yourself, is my alternative one-sided or two-sided? And that was that P1, oh my gosh, minus P2 greater than 0. It was one-sided. So this is our p-value. We don't need to multiply. So that's it. So here, I'm going to go ahead, I'm going to say it was a z-statistic equal to 1.73. That is really super weird. That is the same as the last one, 0.0418. Notice though, it was a one-sided, not two-sided p-value. We did this at the 0.05 significance. Okay, so if we are working at the 0.05 significance level, and we get a one-sided p-value of 0.0418, our p-value is smaller. So p-value is less than our significance level. So we're going to reject. Basically, the smaller the p-value gets in the significance level, the rarer it is, like that what you saw in your sample would happen if the null were actually true. So the more likely we think that the null is bullshit. So there is blank evidence. So I would probably say like moderately strong or strong. Moderately strong. Strong would be okay. Evidence that the proportion of first responder traditional course students that pass the exam is higher than the proportion of first responder hybrid students that pass the exam. And like I mentioned here earlier, I included a disclaimer saying, hey, if they didn't take a random sample of all registrants for this course ever, these inferences may not apply to everyone that would sign up for this course at this hospital. But one thing that is cool is if it came down to like, hey, we said the proportion of people passing is higher in the one class, we can say that is because of the type of class that they were in, because we did a randomized experiment. So, bummer that maybe we can't say this applies to everyone who would take the courses, but we could say of the people who took them at this time, we can say that the difference we saw in the samples of proportions of people that passed, like we could say that was caused by the type of class they took. So then, not sure why we go in this order. We're going to go ahead and find, but a lot of times this is the order. So a lot of places they'd say, hey, is the proportion higher for this group? And so you'd go, oh yes, yes it is. A really, really automatic follow-up for a lot of clients will be like, okay, well, how much higher is it? Estimate how much higher the one proportion is than the other. So they want us to estimate the proportion, the difference in proportions. So given popularity and expense, they were looking at this. They wanted, after being told the proportion of students that pass is higher for the traditional course, the hospital now wants to estimate the difference. So they're like, okay, it's higher, but how much higher? Because if it's only just a little bit higher, they might keep the hybrid course. But if it's a lot higher, they're going to stick with the traditional. Use 95% confidence. So stating my question, since it's an estimation or confidence interval question, this should be an open-ended question, like, hey, what is? And then like the difference in proportions. But you must say which minus which, that kind of idea. So what is the difference in proportion of people that pass their certification exam between all students that take the traditional course and all people taking the new hybrid? I need to specify as traditional minus hybrid. If you don't keep track of this, it is so easy to mix stuff up on the write-up. It is so much harder. So once again, traditional is 1, hybrid is 2. My parameter of interest is the same as before. So I'm interested in P1 minus P2, specifically where 1 is traditional and 2 is hybrid. And so it'll be still the difference in proportion of people that pass between the two courses. I'm still doing traditional minus hybrid. So P1 minus P2, that's my notation. Me talking about in context, the difference in proportion of people that pass their certification exam between all students that take the traditional course and all people taking the new hybrid course. Traditional minus hybrid. Once again, I'm going to stick in here independent populations. That should be on here. So the first are my samples random/representative. This is the same issue that we came across when we were looking at the confidence interval. So sample random, we don't know. They didn't say, they went ahead and they took the course registrants at the time. They had 95 registrants and they assigned them. They did use randomization though. So it's one of those, this may not apply to everybody, but the people that it does apply to, we can say that the difference was caused by the treatment or which class they took. So kind of, it's a mixed bag for condition 1. For condition 2, are sample size big enough? They were last time, but it's worth checking. So we need to have at least 10 successes and 10 failures in both. So if you look at the traditional course, we had 37 people pass, which means we had 10 people not pass. So we do meet the requirements for traditional. If you look at hybrid, we had 30 people pass, which means we had 18 people not pass. So that both of those are at least 10, so we passed there. So just barely, because the one group had only 10 failures, but we do have at least 10 successes and at least 10 failures in both. And then we discussed this one as well. We reasonably have independent populations. We don't believe that people are enrolled in both, that kind of thing. Now, whether or not people talk to each other and work together, that's a whole other scenario. That's a whole other bag of worms is not the right one. Can of worms? I don't know. My idioms are not the best. So my confidence interval level should be 95, which means since I'm doing Z methods, I can just figure out what Z star. That's from that table. I happen to have them memorized, just those 3, but absolutely you can look them up. That's not a problem. You may notice I did not take my inventory here. I will take inventory, but it's going to be on the next slide. So here's my inventory. I had 47 in the first group. I had 48 in the second. The proportion, sample proportion for the first group was 0.787. Sample proportion for the second group was 6.25. Z-star is 1.96 for a 95% confidence interval. Double check. So things to note is your confidence interval does not care what's claimed. It doesn't care about any of it. So P hat T has no business. Like, it's not invited. We don't want it. Anytime that you're calculating confidence interval, it only wants sample information. It doesn't want anything that's claimed. So your claimed value never will be in here. Nothing to do with like that's specific to hypothesis test. So my point estimate here, 0.787 minus 0.625 plus or minus 1.96 times, so 0.787 times 1 minus that, 0.213 over 47 plus 0.625 it's 0.375 over 48. There we go. There's a reason I don't draw the whole square root sign ahead of time. I have no idea how much space I'm going to need. So simplifying, 0.6162, that's my point estimate. So that's the difference in the sample proportions I observed in our actual samples. Plus or minus, my margin of error ends up being 0.180 when I round. So I end up getting negative 0.018 to positive 0.32. So I mean you might notice zeros in here, right? So if I had been running a two-sided hypothesis test, I would be rejecting or failing to reject the null here because zero's in it. But I did a one-sided, and one-sided hypothesis tests don't always agree. So that is worth noting. So it's okay that I have negative and positive values because I'm looking at a difference in proportions. So they could go anywhere from -1 to +1. So as long as these values are in between there, that's okay. I don't need to cut it off at 0 or like I did with the single proportion. And we'll talk about what the heck we do with this interpretation. So negative 0.018 to positive 0.342. So with 95% confidence, the true proportion of first responder traditional core students that passed is estimated to be between 0.018, and see there's a negative sign, so less, and so now my second point, 0.342, and this is higher, this is a positive, so oops, higher than the true proportion of first responder hybrid students that pass. So this is weird because we have a negative and we have a positive, but it's doable by keeping track of, like, if it's a negative, it means less, the estimate is less. If it's positive, it means the estimate is higher. So the first group, the true proportion of the first group, which is the traditional core students that pass, is estimated to be between 0.018 less and 0.342 higher than the true proportion of first responder hybrid students that pass, with a point estimate of, so what I saw in the sample point, so remember it was positive 0.162 higher. So in this scenario, it's really important to not just include the endpoints, but to include higher or lower for each part. So between 0.018 lower and 0.342 higher. That is what we would do for a mixed scenario like that. Might be really useful come next week. Hint, hint. So, or this week, I guess. Still include the disclaimer that if they didn't take a random sample, this may not apply to everybody. But that's really the best we can do, because we still need to do our write-up in terms of the populations. But it is worth probably including a disclaimer that maybe it may not apply to everyone. So that's our bonus example. I hope it was helpful. And well, next week we're definitely going to change tracks. We're going to go look at bivariate data. So post your questions on the content, whatnot, on the discussion board for our lecture, and we will get to you.